The sun of 1274 BC beats down on the granite banks of Aswan with a ferocity that only the children of the Nile understand. At the epicenter of this natural furnace, a scene unfolds that defines the abyss between foreign perception and the systemic superiority of Egypt. Delegates and architects from the lands of the Hittites and the Canaanite city-states are positioned on a wooden platform, observing with a mixture of mockery and disbelief the construction site stretching before them. For these observers, accustomed to mud brick and cedar wood constructions, the ambition of Pharaoh Ramses II borders on clinical madness. They gaze at the colossal pink granite obelisk, a single stone needle still partially embedded in the quarry bedrock. It weighs 300 tons and is made of rock so dense that ordinary bronze tools barely scratch its surface. Laughter among the foreigners is audible. They point to the enormous coils of braided papyrus rope and the ramps of fine sand that the Egyptians are piling around the piece. They think they're going to move a mountain with dry grass and dust, whispers a Hittite engineer, adjusting his heavy tunic, ill-suited for the extreme heat of Upper Egypt. In their view, physics is an immutable law that Egypt is trying to defy with superstition and disordered brute force. The visual contrast is stark. On one side, the foreigners represent the skepticism of a world that still doesn't understand industrial scale. On the other, the Egyptians, depicted as dark-skinned men with dark complexions, textured by sweat and pores visible under the merciless sun, move with a terrifying calm. There is no hurry, for each movement was calculated by scribes on papyrus scrolls months before the first hammer blow. The enemy looks at Egyptian technology and laughs, considering it primitive or impossible, without realizing that they are facing the greatest logistical machine ever assembled by humanity. What the skeptics fail to grasp is the zero-friction system that Pharaoh's engineers are preparing. They see the ropes and think of weakness. They cannot see the science behind the twisting of the fibers that allows them to withstand tons of tension. They see Pharaoh in his royal war attire, hammered gold gleaming against the finest linen, and interpret his presence as mere vanity, when in fact he is the supreme architect, the master strategist, who ensures that every link in this technological chain functions flawlessly. The scorn of the observers is the driving force of this narrative. They believe Egypt has reached its physical limit. They await the sound of snapping ropes, the cries of crushed workers, and the resounding failure that would prove the desert cannot be tamed. But while laughter echoes on the banks of the Nile, the ground begins to vibrate. The Egyptian system, silent and lethal in its precision, is about to be activated. The conflict is set. On one side, the ignorance of those who trust only what they see. On the other, the technical intelligence of a civilization that has learned to sculpt its own eternity. The air in Aswan is so thick, it feels like it has mass, a mixture of dry heat and the mineral smell of crushed granite. As the foreign dignitaries observe from their shaded platform, the discrepancy between what they see and what the Egyptians are accomplishing creates an almost palpable tension. To the observer from the fortified cities of the north, Egyptian technology doesn't seem advanced. It appears at first glance desperately clumsy and slow. They look at the hardwood barges moored on the Nile and see only wide, heavy hulls that seem incapable of any agility. They observe the wooden sleds on which the obelisk will be placed and scoff at the absence of wheels or iron gears, which in their lands are the ultimate symbol of modernity. This superficial view is the first major mistake of those who underestimate the empire. The contrast in perception is, in fact, a clash between short-term technology and engineering for eternity. The enemy looks at the movement of Egyptian workers and sees a sweaty, noisy mass of humanity, but what is operating there is a living algorithm. Each group of 100 men functions like a piston in a human internal combustion engine, coordinated by visual and rhythmic signals that ensure the applied force is constant and never impulsive. While foreign military tactics rely on abrupt movements and impact force, Egyptian engineering is based on managing inertia. The central object of this technical discord, the 300-ton obelisk, appears to critics like a dead stone that will never move. They comment amongst themselves on how the project seems stagnant, how each centimeter gained takes hours of effort that seem disproportionate. To a Hittite general accustomed to the speed of his light chariots, that transport operation seems like a relic of a primitive past. They fail to grasp that the Egyptian slowness is, in fact, total control over gravity. A millimeter error in a high-speed maneuver would destroy the monument, and the Egyptians know that true technology is not the one that moves the fastest, but the one that never fails. Furthermore, there is the aesthetic and material shock. Foreigners bring with them objects of cast iron and bronze, tools that gleam and appear sharp. Seeing Egyptian workers using dolerite balls, extremely hard circular stones, to excavate granite through repeated impacts, visitors feel an almost childlike technical superiority. They see stones striking stones and conclude that Egypt has stopped in time. What they ignore is that dolerite is the only substance capable of wearing down pink granite without breaking the tool every 5 minutes. It is the application of material science in its purest form, using natural hardness to overcome structural resistance. In this setting of merciless sun, the skin of the Egyptians, dark-skinned men with strong, realistic features, shines like polished granite itself. There is a symbiosis between the creator and the work that foreigners could never emulate. While the foreign observer feels like an intruder in that hostile climate, the Egyptian engineer uses the heat to his advantage, knowing exactly how the thermal expansion of the rock can help or hinder the cutting. The contrast in perception reaches its peak when visitors realize that there are no cries of despair or cracking whips as they imagined. There is only the rhythmic, industrial, and hypnotic sound of a nation that has transformed logistics into a form of worship of the pharaoh. What seems clumsy to the world is, in fact, the mechanics of immortality being executed with a precision that the modern technologies of the north could never sustain. The heat of Aswan is not merely a climatic condition, it is a merciless clock dictating the rhythm of survival and glory in ancient Egypt. While foreign engineers continue to cast their doubting glances over the construction site, an invisible tension begins to dominate the atmosphere. It is no longer just a demonstration of technical skill or architectural ego. The Obelisk project now faces the face of nature in its most absolute and inevitable form, the Nile's water cycle. In Ramses II's Egypt, engineering is not an isolated science, it is enslaved to hydrology. The real threat looming over the expedition is the deadline imposed by the annual flood, the Akhet. If the 300-ton monolith is not placed on the barge at the exact moment the waters reach the critical level in the artificial canals, all the effort of months will be swallowed by the silt, or worse, the monument will remain stranded for another whole year under the scorching sun, becoming a symbol of failure before gods and men. The risk is systemic. To the untrained observer, the Nile River appears as an endless, passive road, but to the actual architect, it is an indomitable force demanding industrial precision. If the barge is loaded too early, the wooden structure may not support the weight without the aid of full buoyancy. If it is too late, the current will become too violent to navigate with such an unstable load. The deadline is a blade to the throat of every worker. It is in this scenario of urgency that the contrast between Egypt and its neighbors becomes even more dramatic. While rivals to the north believe that the Egyptians are merely waiting for luck, the reality is that they are mobilizing a brutal logistical network to beat the clock. The threat is also political and strategic. Egypt is living through the golden age of the New Kingdom, a period where the image of power is as vital as power itself. Ramses II ordered this obelisk to be erected in Thebes to celebrate the Opet festival, an event that reaffirms his divine connection and his ability to uphold Ma'at, the cosmic order. Failure to deliver this piece of engineering would not be merely a logistical error, it would be a crack in the pharaoh's image of invincibility. The foreign spies present at the site know this. They observe the rising river, hoping to see chaos ensue. They expect the papyrus ropes to give way under the pressure of the water, the sand ramps to crumble, and Egyptian arrogance to be buried under tons of pink granite. Within this context of imminent danger, human mobilization reaches industrial levels. Thousands of workers, represented as dark-skinned black men with bodies sculpted by exhausting labor, work in uninterrupted shifts. The sweat that runs from their pores is not only a result of the heat, but also of reverential fear and military discipline. Every second counts. The real threat is not just gravity, but the logistics of survival. If the navigation channel is not dredged in time, the colossal barge, built with hardwood and reinforced with moorings that defy the logic of the time, will not have enough depth to float. The climax of this topic lies in the realization that Egypt is not only fighting against the stone, but against geological time itself. The sound of dolerite tools striking the granite grows more frantic, a warlike percussion echoing off the quarry walls. The foreigners seated on their platforms begin to feel the unease. They realize that although the river is rising and the threat of natural disaster is imminent, the Egyptians show no panic. There is a method to the madness. There is a hidden science in the way they monitor the water level with precise nilometers. The real threat, which should paralyze any other civilization, is merely revealing the technical superiority of an empire that has learned to transform natural disasters into engineering opportunities. The stage is set. Nature has given its ultimatum, and now the pharaoh's technical genius must respond with a perfection that allows no errors. While foreign observers awaited the imminent collapse of the operation under the crushing weight of physics and the pressure of time, Ramses II's engineers prepared to unveil a technological intelligence that the enemy could never have imagined. What the outside critics didn't know was that Egypt didn't rely solely on brute muscle power. They operated under a precision engineering system that used the laws of nature as leverage tools. The image of thousands of workers pulling ropes was merely the visible face of a far more complex, invisible machine. The secret lay in a science that blended rudimentary hydrostatics with absolute control of friction. Foreigners looked at the sand ramps and saw only clumsy mounds of earth, but what they didn't know was the exact composition of that sand and the controlled emptying method for positioning colossal loads. The Egyptians had developed a system of internal sandboxes that functioned like a reverse hydraulic elevator. By removing sand from specific channels beneath the monument, they allowed the 300-ton obelisk to descend millimeter by millimeter with a precision that iron tools could never achieve. It was gravity being used to defeat gravity itself. Furthermore, there was the mystery of the ropes. The Hittites and Canaanites knew about ropes, but they did not know the Egyptian science of traction. The ropes used were not simple braids of fibers. They were high-performance textile engineering. Made of papyrus and palm fibers, they were treated with oils and resins to prevent drying under the merciless Aswan sun and to ensure that elasticity was maintained under extreme tension. What the enemy saw as dry grass was, in fact, an ancient steel cable capable of withstanding braking forces that defied the technological understanding of any other people of the time. Another closely guarded secret by the pharaoh's scribes was the use of the rocking cradle. Egyptian engineers didn't try to drag the stone statically. They used laminated wood sleds, built with perfect joints that allowed for even weight distribution. Underneath the tracks of these sleds, a constant mixture of water and fine clay, Nile silt, was poured by specialists, creating a layer of lubricant that reduced friction by up to 50%. To the eyes of the critics on the podium, it seemed only that the workers were ritually pouring water, but in reality, they were creating an artificial ice rink in the middle of the desert. What they also didn't know was about applied geological intelligence. Before the first blow of dolerite was struck in the quarry, Ramses' architects had performed resonance tests on the rock to identify micro fissures invisible to the human eye. They knew exactly where the stone was strongest and where it would fail. This wisdom allowed them to carve monoliths so long and thin without them breaking under their own weight during transport. While other nations attempted to build with small, stacked blocks, Egypt mastered the art of the monolith, the ability to treat the mountain as a single, malleable piece. Finally, there was naval intelligence. The barges that foreigners considered clumsy were, in fact, marvels of flat-bottomed naval engineering. They were designed with an internal weight compensation system. Before the obelisk was loaded, the barge was filled with smaller stones so that it would sink to the canal bed. As soon as the obelisk was positioned on it, the smaller stones were removed, allowing the barge to gradually rise with the Nile's level, using the principle of buoyancy to lift 300 tons without a single crane being needed. The foreigners' laughter began to fade when they realized that the Egyptian magic was, in fact, superior mathematics that they could not decipher. The revelation that behind the stone or wood there was an unsurpassed technological intelligence transformed the initial disdain into a reverential and terrified silence. Behind every hammer blow and every inch of the obelisk's movement resided the mind of a master strategist operating in a realm of thought far beyond the comprehension of foreign observers. In the Egypt of Ramses II, design was not merely a matter of aesthetics or artistic preference. It was an instrument of domination and a manifestation of divine will on earth. The origin of the design of this colossal monument dates back to the papyrus offices of the royal architects, men who were not only builders, but high priests of mathematics and sacred geometry. For them, the obelisk The benben was a physical representation of a petrified sunbeam, and its technical execution had to be as perfect as the light that inspired it. The royal architect, often a high-ranking nobleman or the pharaoh himself in his role as supreme commander, acted as the brains of a national organism. While engineers from neighboring nations focused on solving immediate construction problems, the Egyptian designer designed with a vision spanning millennia. The origin of the obelisk's design took into account not only the strength of the granite, but also the symbolism of power. Ramses II didn't just want a standing stone, he demanded a tool of psychological intimidation. The design was conceived so that when the sun reached the electrum-coated top, an alloy of gold and silver, the brilliance would be visible for miles, symbolically blinding anyone who dared to question Egyptian authority. At this stage of the narrative, the contrast between Egyptian sophistication and foreign rusticity reaches a critical point. The architect is depicted as a black man with noble and decisive features, whose hands, though they do not touch the stone, move mountains through calculation. He uses precision tools such as hardwood squares and granite plumb bobs, which allow for a virtually non-existent margin of error. The obelisk's design included a subtle covering, an almost imperceptible curvature on the stone faces, to compensate for the optical illusion that makes large structures appear concave when viewed from below. This level of visual refinement was something that Hittite architects focused on rough and functional walls could not even conceive of. Planning began long before the first extraction at the Aswan quarry. The architect studied the local geology for years, searching for the perfect vein of pink granite that would withstand the stress of being transformed into a 30-meter needle. The design required the base to be slightly wider than the top, creating a center of gravity that would allow the monument to withstand earthquakes and millennia of erosion. Each hieroglyph carved into the surface was not merely an inscription, but part of the structural integrity of the piece, calculated not to weaken the monolith. What the enemy saw as decoration was, in fact, the codification of a civilization that mastered the fusion of form, function, and eternity. The origin of this design was also deeply linked to war logistics. The pharaoh, as a master strategist, saw the obelisk as an extension of his military campaigns. Just as a chariot was designed to be light and fast, the obelisk was designed to be transportable despite its colossal mass. The use of laminated wood in transport sleds and the calculation of weight distribution in barges were the result of a technological intelligence that treated Egypt as a large industrial factory. The design did not end with the stone. It extended to ramps, canals, and tools. When foreign observers looked at the plans drawn on papyrus scrolls, they saw only lines and figures. They couldn't decipher the complexity of the volume and density equations that ensured that impossible weight would float. To the ancient world, Egypt's success seemed like magic or divine intervention. To the royal architect, it was simply the rigorous application of a design that placed human genius above the limitations of matter. The origin of the design was ultimately proof that Egypt was not building merely for the present, but to ensure that, even after millennia, the world would still awe at its technical superiority and tremble before its vision of immortality. The perfection that foreigners witnessed on the banks of the Nile did not spring from nothing. It was forged in centuries of brutal experimentation, catastrophic errors, and a human and material cost that few civilizations would dare to pay. For Ramses II's obelisk to be moved with clockwork precision, generations of Egyptian engineers had to face failure. The learning curve of pharaonic engineering is etched in the scars of the quarries themselves and in the abandoned monuments that dot the Egyptian landscape. What Hittite and Canaanite observers saw as natural success was, in fact, the result of a technical resilience forged in disaster. The most emblematic example of this learning curve is the so-called unfinished obelisk, which still rests on the bedrock in Aswan. This giant, which would have been the largest monolith ever erected by humanity, standing almost 42 meters tall and weighing 1,200 tons, serves as an eternal reminder that even Egyptian genius has its limits. During its extraction, a gigantic fissure appeared in the pink granite, condemning the project to immediate abandonment. For the royal architects, this was not just a waste of resources, but an unprecedented geological lesson. They learned that granite, despite its hardness, possesses internal stresses that can be catastrophically released if the cutting angle does not respect the mountain's lines of force. Every centimeter of Ramses' obelisk was designed with the knowledge gained from this colossal failure. The learning curve also involved perfecting the tools. Initially, attempts to cut granite with pure bronze resulted in useless wear of the metal and almost no progress. It was through observing natural abrasion that the Egyptians discovered the secret to precision cutting, the use of quartz sand as an abrasive. They realized that the metal served only as a guide, while the tiny grains of sand under pressure did the real work of grinding. Thousands of hours were lost and hundreds of tools were destroyed until the exact ratio of pressure and lubrication was mastered. The magical technique that foreigners so feared was, in fact, the sum of 1,000 years of trial and error accumulated on papyrus scrolls kept in the houses of life. The human cost of this learning process was equally brutal. The logistics of mobilizing 10,000 men to move a single piece of stone required an organization bordering on military perfection. In the early centuries, accidents involving collapsing ramps or ropes breaking under tension were common. Each worker crushed under a granite slab resulted in a complete overhaul of safety and engineering protocols. The Egyptians perfected the technique of rope braiding, creating composite cables that distributed weight evenly, reducing the risk of sudden breakage. What observers saw as a fluid execution in Aswan was the result of industrial safety protocols developed through past tragedies. The very architecture of the transport barges underwent a dramatic evolution. Early attempts to transport smaller obelisks resulted in embarrassing shipwrecks, where the weight of the stone would break the keel of the vessel or cause a fatal capsizing during loading. The learning curve taught the Egyptians to build barges with internal bracing systems using cedar beams from Lebanon arranged in trusses that absorbed the structural deformation caused by the 300 tons of the monolith. They learned to read the river not just as a path, but as an active element of engineering, timing the barge's entry into the canals with second-level precision to take advantage of the peak tide. To the foreign observer, Egyptian learning was invisible. They saw only the final product, the finished glory, and concluded that Egypt possessed divine secrets. However, the true secret was the discipline of documenting every mistake. Ramses II's architects looked at the crooked pyramids of their ancestors and the cracked obelisks of previous dynasties, not with disdain, but with the gaze of a student. They understood that technological superiority is not the state of never making mistakes, but the systemic ability to never repeat the same mistake. In moving the 300-ton obelisk, they were carrying not just stone, but the accumulated wisdom of millions of hours of work, sweat, and resilience of an empire that decided that nature would not be an obstacle, but a raw material to be mastered through accumulated knowledge. The moment of truth has arrived on the banks of the Nile. The silence hanging over the port of Aswan is as heavy as the 300 tons of pink granite that now rest at the edge of the launching ramp. This is the climax of months of planning, the ultimate test where the scribe's theories and the architect's calculations confront the brutal reality of physics. The foreign observers, who once laughed openly, are now mute. They huddle on their platforms, their eyes fixed on the colossal mass of stone defying gravity. The laughter has vanished, replaced by anxious anticipation. They await disaster, the snapping of ropes, or the shipwreck that would prove Egypt has tried to go too far. The loading operation is a choreography of power and millimeter precision. The obelisk, placed on the hardwood sled, begins its descent towards the gigantic barge waiting in the artificial canal. The zero-friction system, developed in secret, comes into action. Experts pour Nile silt under the rails, creating a lubricating layer that makes the stone slide with terrifying smoothness. Thousands of workers, black men with taut muscles and skin glistening under the merciless sun, hold the reinforced papyrus ropes. They are not just pulling, they are controlling the fall. Every movement is dictated by the rhythm of drums and papyrus signals, ensuring that the monolith does not gain an inertia that no one can stop. The critical point occurs when the obelisk's center of gravity begins to shift from the ramp to the barge's deck. This is the instant the wood creaks with a sound like the cry of a wounded giant. The vessel, built with an internal bracing system that absorbs extreme structural stresses, tilts slightly under the weight. It is here that the Egyptians' technical magic is devastatingly revealed to foreign perception. They had filled the barge with smaller stones so that it would settle on the bottom of the canal. As the obelisk enters, the weight is transferred and the vessel does not rock sideways. It remains stable, acting as a solid extension of the land itself. As the monolith advanced, The Egyptian genius removed the ballast stones from the barge with industrial speed. The physics of buoyancy began to work in the pharaoh's favor. With the controlled rise of the water level in the canal, the barge began to slowly rise, lifting the obelisk off the ramp and assuming its full weight. The foreigners watched speechless as that stone needle, which they considered immobile and impossible to transport, began to float. There was no expected collapse. No ropes broke. What happened was irrefutable proof that Egypt triumphed not only through bravery, but through inexhaustible technical skill and mastery of the laws of nature. This moment is not merely an engineering feat. It is a demonstration of systemic superiority. While other nations struggle to move blocks weighing a few tons, Egypt is transporting a monolith that could crush an entire army as if it were a feather on water. The shock on the faces of the observers is Ramses II's greatest trophy. Terror sets in as they realize that if Egypt can move mountains with such ease to build monuments, it can do the same to destroy its enemies. Brutal logistics and technical precision have transformed the Nile River into an assembly line of divine glory. The obelisk is now sailing, ready to cross the horizon towards Thebes, leaving behind a trail of disbelief and the silence of those who have just witnessed the impossible become reality through human ingenuity. To the casual observer, the obelisk's floating seems like a miracle. To the Egyptian strategist, it was a triumph of applied arithmetic and materials physics. In Ramses II's Egypt, engineering wasn't based on guesswork, but on a mathematics of construction that operated with heavy numbers and a precision that defied the logic of the time. While foreign engineers relied on intuition or trial and error methods, the pharaoh's scribes used calculations of volume, density, and displacement that would guarantee the work's eternity. To move 300 tons of pink granite, one first had to master the mathematics of the impossible. The first major challenge was the specific gravity of Aswan granite. Each cubic meter of this stone weighs approximately 2,700 kilograms. With an obelisk 30 meters high, the volume calculation needed to be exact, down to the last cubic centimeter. Any error in calculating the center of gravity would result in a catastrophic disaster. The monolith could topple during lifting or, worse, crack in half due to uneven distribution of internal stress. Egyptian architects, black men of refined intellect, used complex unit fractions to determine the exact point of equilibrium, ensuring that the weight was evenly distributed over the transport sleds. Mathematics also dictated human logistics. To drag a 300-ton monolith, it wasn't enough to simply put more men on it. There was a cadence of pull, a mathematical proportion between the weight of the load and the traction exerted by each worker. The Egyptians knew that an average worker could exert a constant traction force of approximately 30 to 50 kilograms. Doing the math, thousands of men would be needed, pulling in perfect synchrony. However, Egyptian mathematics went further. They calculated the coefficient of friction. By using Nile silt and water as lubricants, they drastically reduced the force required, allowing a smaller, more coordinated workforce to accomplish what seemed to require an endless army. The millimeter-precise joints were another detail that silenced the skeptics. When the obelisk arrived at its destination in Thebes, it needed to be erected on a granite base. The mathematics of the construction demanded that the contact surfaces be so flat that the margin of error was less than the thickness of a human hair. Without the use of iron tools, they achieved this level of polish using quartz abrasives and wooden squares, measuring the inclination with water levels. If the base was even a millimeter out of plumb, the top of the obelisk, 30 meters above, would be dangerously tilted, compromising the structure and aesthetics of the monument. Another brutal fact was the logistics of time. The mathematics of the Nile was the nation's clock. Scribes calculated the speed of the current and the volume of water displaced by the barges. For a 300-ton obelisk to float, the barge needed to displace a volume of water equivalent to its total weight, plus the weight of its cargo. This resulted in colossal vessels, veritable floating islands of hardwood. The industrial scale of mobilization to build such barges involved calculating thousands of meters of planks and tons of papyrus ropes, all planned with a precision that allowed no waste. On the construction site, the sound was not one of chaos, but of a mathematical orchestra. The rhythm of the drums that coordinated the doorknobs was based on precise timing to prevent the load from gaining excessive speed on inclined ramps. The mathematics of construction was the language of order over the chaos of the desert. While foreigners looked at the work and saw only stone and people, the Egyptians saw vectors, tensile forces, and volumes. This technical superiority, based on weighted data and a rigorous application of geometry, was what ensured that Egypt remained the greatest technological power of antiquity. The obelisk was not just a monument, it was mathematical proof that human genius, under the direction of a strategic pharaoh, could bend physical reality to its will. To support Ramses II's technological ambition, Egypt operated not only with isolated artisans, but with an industrial-scale logistics machine that mobilized resources on a scale never before seen by its contemporaries. The construction and transport of a 300-ton obelisk required an infrastructure that stretched for hundreds of kilometers along the Nile Valley, transforming the kingdom into a vast assembly line. What foreign observers saw as a singular event was, in fact, the end result of a brutal mobilization of human, material, and natural resources, coordinated with the precision of an empire that treated logistics as a science of domination. The scale of this operation began in the quarries of Aswan, which functioned as veritable mass production factories. It wasn't just about carving a piece of granite, it was about sustaining a population of thousands of laborers, engineers, scribes, and soldiers in the middle of an arid desert. To keep this workforce operating under the merciless sun, Egypt built an unprecedented supply network. Barge convoys loaded with grain, meat, and beer arrived daily from the granaries of the Delta and the farms of Middle Egypt. Waste management, the maintenance of copper tools, and the health logistics for treating injuries in a high-risk work environment were managed by a state bureaucracy that allowed no room for error. Tool production was, in itself, a heavy industry. Although the cutting of granite was primarily done with dolerite stones, the finishing and detailing required the extensive use of copper and bronze chisels. Because these metals were relatively soft, they wore down quickly against the density of the pink granite. This necessitated mobile forges operating 24 hours a day near the quarry, where skilled blacksmiths melted down and resharpened thousands of tools daily. The logistics of supplying coal and ore to these forges involved trade routes that crossed the Eastern Desert and the Red Sea, proving that a single obelisk was the epicenter of a globalized economy. Beyond extraction, textile logistics were vital. As already discussed, papyrus and palm fiber ropes were the steel cables of the time. To manufacture the miles of rope needed to withstand the tension of 300 tons, vast areas of the Nile banks were dedicated exclusively to the cultivation and processing of papyrus. Rope factories operated on an industrial scale, braiding fibers in specific thicknesses for different functions, from thin maneuvering cables to master ropes with the circumference of a tree trunk. Quality control was rigorous. A single defective fiber in a master rope could cause a domino effect that would destroy months of work and cost the lives of hundreds of men. The land transport infrastructure was another demonstration of brute force. To move the monolith from the quarry to the riverbank, the Egyptians not only cleared the path, they built dirt roads reinforced with wooden sleepers, creating a solid foundation that prevented the colossal weight from sinking into the desert sand. The logistics of moving these sleepers, which were removed from the back of the sled and placed in front in a continuous cycle, required perfect mathematical coordination. Thousands of workers operated in synchrony, like the gears of an organic machine, moving tons of wood and stone under the watchful eye of foremen who used percussive rhythms to maintain the industrial cadence. Finally, there was naval and hydraulic logistics. Egypt didn't just build boats, it reshaped geography. For the obelisk's shipment, artificial canals were excavated and sluice gates were erected to control the flow of the Nile. The construction of the transport barge, made with imported hardwoods like cedar from Lebanon, required the work of armies of carpenters and caulkers. The mobilization of resources on an industrial scale to support this technology, from massive quarries to naval fleets and weapons factories to the guard protecting the treasure, was what set Egypt apart from any other civilization. The proof of superiority lay not only in the stone erected, but in the empire's inexhaustible capacity to sustain the impossible through a logistical system that ignored the limitations of nature and time. The moment laughter dies is the moment power becomes absolute. On the observer's platform in Aswan, the air, once light with the sound of jeers and side conversations about supposed Egyptian arrogance, suddenly became heavy, almost unbreathable. As the 300-ton obelisk, a mass that should have been immobile according to the laws of nature known to foreigners, began to move with a silent, predatory fluidity, the psychology of that audience shifted dramatically. The smiles of the Hittites and the disdain of the Canaanites were replaced by a mask of icy shock. The terror did not come from a war cry or a cavalry charge, but from the realization that Egypt operated on a level of technical reality they didn't even know existed. This shift in perception is the turning point where the observer realizes they cannot defeat the Egyptian system. For the enemies, the real danger was not the stone itself, but the mind capable of making it float. They looked at the thousands of Egyptian workers, black men with determined features and sweat-drenched bodies, and no longer saw merely slaves or manual laborers. They saw the gears of a perfect state machine, capable of mobilizing the very geology of the continent to fulfill the desires of a single man. The terror stemmed from the understanding that if Pharaoh Ramses II possessed the technology to move a granite mountain and float it down the river, he possessed the logistical capacity to crush any foreign resistance through industrial attrition. The visual shock was devastating. To see the monumental barge, laden with a weight that should have sunk any known vessel, float smoothly toward the main Nile canal, shattered the foreign generals' confidence in their own tactics. They believed that war and construction were made of impulses and brute force, but what they witnessed was the application of an infallible mathematics of destruction and construction. The silence of the workers, moving in perfect synchronicity, without the chaos or shouts common in their own construction sites, was proof of a military discipline applied to engineering. The enemy realized that they were not facing a primitive people with ropes, but a civilization that had transformed nature into a tool of psychological domination. The terror also lay in the precision. The fact that the obelisk not only moved, but moved exactly where the architects planned, without wobbling, without errors, and without accidents, revealed total control over the environment. For a foreign spy, this demonstration of power was a warning. Egypt didn't need endless armies if it possessed an engineering prowess that made the impossible an administrative routine. The laughter of the critics turned to silent dread as they imagined what that same technical intelligence could design for the battlefield. If they could move 300 tons of stone with ease, what would they do with the speed of chariots or the rate of fire of their composite bows? At that moment, the figure of Ramses II, positioned on his golden platform, ceased to be seen as a vain pharaoh and was recognized as the master of an indomitable machine. The sun beating down on the polished granite of the obelisk created a brilliance that seemed to blind the skeptics, a light that symbolized the victory of Egyptian intelligence over external ignorance. The shift in perception was total. Egypt was not merely a land of ancient monuments. It was the world's technological superpower, a nation that had conquered the system because it had become the system itself. The terror that foreigners took back to their lands was not that of military defeat, but of the realization that they were centuries behind a civilization that had already learned to sculpt eternity on an industrial scale. The definitive proof that the Egypt of Ramses II was the hegemonic power of the ancient world lay not only in the aesthetic beauty of its monuments, but in its capacity to sustain what we would now call a war of technological attrition. Egyptian superiority was not a fortuitous event or a stroke of architectural luck. It was the manifestation of an inexhaustible technical system that possessed the depth of resources necessary to absorb any failure and transform it into a logistical advantage. While rival nations operated with limited resource budgets and technologies that depended on individual artisans, Egypt had industrialized the impossible. Attrition and systemic superiority were the pillars that allowed the pharaoh to project power through 300-ton stones. To the foreign observer, the Egyptian mobilization seemed a waste of energy. They didn't understand that the true strength of an empire lies in its redundancy. When a rope broke or a barge suffered structural damage, the system didn't stop. There was always a papyrus rope factory ready to provide immediate replacements. There was always a reserve of highly skilled manpower ready to step in. This ability to maintain constant technical pressure on the environment and on enemies is what defines attrition superiority. Egypt won not only because it had the best engineers, but because it had the best support system for those engineers. Systemic superiority manifested itself in standardization. In the quarries of Aswan, dolerite tools and copper chisels were produced and distributed following rigorous protocols. This ensured that work never ceased due to a lack of equipment. While a Hittite king would need months to organize the transport of a heavy load through hostile territories, the pharaoh possessed a permanent hydraulic highway, the Nile. The integration between nature and man-made infrastructure was so perfect that the river functioned as a continental-scale conveyor belt. This brutal logistics allowed Egypt to maintain construction sites in Abu Simbel, Thebes, and the Delta simultaneously without the kingdom's economy collapsing. Attrition was also evident in the management of human capital. Egypt did not rely solely on brute force. It employed specialists at every link in the production chain. There were dark-skinned, dark-featured black men dedicated exclusively to measuring the density of sand. Others focused on lubricating sleds, and scribes who accounted for every gram of rations distributed. This specialization created an efficiency that reduced material costs in the long term. The enemy, observing the monumental scale of the work, imagined that Egypt was exhausting its resources. The reality was the opposite. Each major engineering project served to train a new generation of specialists and to refine supply chains, making the empire increasingly efficient and dangerous. On the battlefield, this technical superiority translated into unwavering resistance. An army that can build pontoon bridges in hours or erect brick fortifications and moats like those at Buhan in record time is an army that cannot be defeated by conventional tactics. Egyptian systemic superiority was a clear message to the world. Egypt possesses the means of producing glory. If an obelisk were lost in the river, the pharaoh would have the resources to extract and transport another immediately. This inexhaustible capacity for technical persistence generated psychological terror in adversaries who perceived that any victory against Egypt would only be temporary, as the pharaonic system would continue producing, building, and advancing. The Egyptian victory was therefore a victory of intelligence applied to logistics. Systemic superiority proved that the empire depended not only on the bravery of its soldiers, but also on the robustness of its workshops, quarries, and administrative minds. The obelisk calmly sailing down the Nile towards Thebes was the ultimate symbol of this reality. It represented a system that had learned to master matter, time, and manpower on a scale that the rest of the ancient world could not even dream of. In the end, the Egyptian attrition proved that true superiority lies not in the initial impact, but in the ability to maintain technical excellence indefinitely, ensuring that the pharaoh's banner continued to fly over the horizon while rival empires crumbled under the weight of their own inefficiency. The obelisk that once floated on the waters of the Nile was not merely a piece of granite. It was a time capsule laden with the intelligence of a civilization that refused to be forgotten. Millennia have passed, empires of iron and steel have risen and fallen, but the stone needles of Ramses II remain standing, defying erosion, gravity, and the very logic of history. The legacy of this technology haunts us today, not only for its monumental scale, but for the mystery of its execution. How did a people, armed only with stone and wooden tools, achieve a precision that still requires the use of modern cranes and high-performance computers to replicate? The answer lies in the systemic superiority of a nation that treated engineering as a path to divinity. Today, when we observe these monuments in city squares like Paris, Rome, or London, or even in their original locations in Thebes, we are confronted with our own limitations. The legacy of the 300-ton obelisk is the silence it imposes on modern skeptics. It is physical proof that human ingenuity, when organized under a strategic vision and brutal logistics, can overcome the impossible. The Egyptians did not build only for their time. They designed the future, ensuring that their mark would be imprinted on the skin of the planet for all eternity. Each hieroglyph perfectly preserved in the pink granite is a code of technical superiority that we are still trying to fully decipher. This feat of engineering teaches us that true technology is not defined solely by the complexity of machines, but by the depth of vision. Egypt overcame the barrier of time because it transformed stone into a manifesto of power. The legacy of Aswan and Thebes is a constant reminder that resilience and systematic intelligence are the only paths to immortality. If the ancient world laughed at papyrus strings, the modern world bows before the needle that still points to the sun, reminding us that, under the command of a pharaoh, humankind was capable of shaping the mountain itself. If you feel the weight of this history and want to understand how human ingenuity overcame the impossible and secured eternity, you need to delve into the secrets the sand tried to hide. The journey through Egypt's technical superiority is only beginning, and each detail revealed is proof that we are not dealing with the past, but with a lesson for the future left to us millennia ago. Subscribe to the channel, The Mysteries of Ancient Egypt, so you don't miss the next secret revealed. Here we unearth the mathematics of destruction, the logistics of construction, and the power of the gods who walked the earth. Click the subscribe button and turn on notifications to ensure you're there when the next piece of this monumental puzzle falls into place. Egypt awaits you.